So today, as I said, we'll do a review on virtual memory and cache, which is the last section of this lecture. And this is one of the more important topics going forward. Once you're in the operating system, once you're in parallel programming, once you're in any class that want to extract performance, you need to know how cache works. All right. So after that big claim of mine, let's do a review. Cache organization. This is, I think, the third time you see this slide. So I'm gonna go quickly. Basically, this is how cache works. You have cache block, which you would then specify what's the size of this cache block. It can be 64 bytes. It can be 32 bytes. In our assignment, this is 32 bytes. Then there are n cache set. Each set treated as a mathematical definition of a set. What is a set? Basically, it contains items. If you go to the same items, you don't increase the element of the set. If it's a different items you insert, you put it in there. But the set has a size. The size is called associativity. So in this example, what's the associativity of this example? Cache. Can someone tell me? Yes. So why don't you answer two? That's correct. Basically, this is a two-way cache, right? So think of it as you have two seats on the bus, right? And only two people can sit on those two seats. If you have the third person coming in, someone has to be evicted. Someone would get out of their seat, make room for the person coming in. Assignment 4, you are going to build two levels of cache. The first level is exactly like this, but you expand the set from 0 to 7 now to 0 to 15. That's all. We'll talk about this a little bit once we are in the part we discuss the assignment. The second thing that I want you to know is there's a problem called set thrashing, and this is a problem that can happen on your program. When you write a program and you want to kind of squeeze out performance, right? This can happen. Basically, you have a four-way cache, you have A, B, C, D, and E as a access pattern, right? You loop to 5 elements. Each element belong to the same cache set, but it just happened that you have four-way cache. So what happened here is basically E comes in, replace A, right? A go out, this is E. And then the next time A comes in, oh, A is not here, so it would replace B, and then B would replace C, C would replace B, and then E get now replaced by D, and A would get replaced by E again. So over here, you can see that there's no cache hit whatsoever, even though you have a four-way cache, right? Four-way cache is actually pretty costly to have on your CPU. But you don't get any benefit. You don't get to use the cache at all, right? So that's pretty useless. In this case, our policy that we learned in class, least recently used, becomes ineffective, right? So our extra credit actually involves these policies. Basically, your job is to design something that is different than our default policy. We'll talk about this toward the end of this lecture. And in here, what you might notice is if you just replace things randomly, you would probabilistically, there's non-zero chances that you get some hits, right? Then it means that if you rework things randomly, you get better performance than least recently used. Then after we're done with caching, any question about caching? Because it seems like I spent 3 lectures on that, so I'm not gonna pound the topic again. That's already in class exercise. Any question about caching that you want to you want to ask before we talk about the CacheLab toward the end of this lecture? Nope. Okay. So then we talk about the virtual memory. So in virtual memory, the reason why I put this slide first is this is kind of what I want to get out of you when you are taking the exam. Most of That's a really bad way to phrase it, right? But first of all, hopefully you know the benefit of virtual memory. There's already slides on that. If you read the slides or if you watch the video, you would then notice that, okay, virtual memory is pretty magical, but you need to know how it works. And this is how it actually works. You have a virtual address here, right? Over here is a virtual address. What you do is you break the virtual address down into multiple chunks. Right? Over here is 32 bits. With x86, if you read the spec sheet, it will say there are two levels of page table. Two levels of page table means that now we have to split your address into three chunks. The first chunk is called page offset. These are the bits that go into your physical address as well. Then there's level 1 and level 2 index bits. Those two are used to index into which entry in my page table that I am going to get the value from. In the in-class exercise on Friday, I would basically borrow the exam question from the last semester, and I'll ask you to do this page walk. Basically, I'm going to dump DRAM in your face and say, okay, this is where the first level of the page table is located. Find your physical address. That's a totally legit question I can ask on your exam. The content of the PTE would then use to look up the next level page table, which then you go based on this level too, right? It comes down here. And then when you get PTE4, this PTE4 get copied right here. You concatenate the offset right here, and then you get the physical address, PA. That's it, right? These location, the physical address tells you where in DRAM I am accessing. Where in DRAM I'm accessing. If you somehow love computer architecture in the future and you take like graduate level class, you would then notice that this physical address doesn't really tell you the exact location, but as of now, treat it as this is the address in DRAM. The reason why they're not going through the exact location is basically to improve the lifetime and reliability of your DRAM. There are actually like circuit and physics reasons behind it, and we're not going to cover in this class. If you're interested, attend office hour in ComArt or office hour in this class. I'm working on this area, so if you have questions, I'm more than happy to answer. TOB structure. This is another thing we talk about, right? What is a TOB? Can someone tell me what is a TOB? All right. Okay, how about this? I'll make sure I ask this question on your exam. This is going to be your free point. What is the TOB? All right. I know. I'll mark it here. What is a TLB? Can't be more obvious than this. Can someone tell me what is the TLB? I'm not going to answer now that I tell you it's going to go into the final exam until someone here answer. Okay, translation look-aside buffer. Awesome. All right, you get the acronym. What does it do? There are the answer, like 5-word answer for this. Okay, actually, you all have a really good like summary of that. First answer is done privately, so let me talk it out. The answer is memory cache that reduces time to access memory. Yes, to be more precise, that memory, the access memory, is actually accessing the page table to get your physical address. The second answer is a table to look up the one-to-one virtual address to physical address. That's probably the most direct answer. Basically, think of it this way. It's a cache for your virtual address to get the physical address. Specifically, it's a cache where you put in virtual page number, you get physical page number. Actually, let me delete it. Let me just make it really clear here. Okay. This is your TLB. Input, what is our input? Virtual address, what do you get out of it? Yep. And inside here, is this in the cache block granularity or is this in the address granularity? Or is this in the page granularity? Yep. One of the private answer is in page granularity. You're correct. Basically, one single entry cache the entire page. Why is that the case? Because virtual address already have the page offset, so there's no point caching anything in a finer grain than that page granularity because you have that information already, right? So this is what basically what you get from the TLB. Hopefully you can answer your exam for this question. 3 points, all right? Another answer is to reduce the time used to access the user memory location. Yes, basically it reduces the time to get your physical address. Physical address is just to get the location. Can you draw this on the exam? With some explanation, that's an intentional reason why I'm not circling anything here. For example, I could have circled the word page. So I leave it as is so that you kind of like need to, if you go and study it again, you're confused about is it cache block, address, or page, check with me or check with your friends. But so yeah, the TLB structure treated as basically is a caching structure, but used for virtual memory. It cached the virtual address, translation into physical address. Right? Why is this good? If I have two levels of page table with no TLB, what's the minimum number of DRAM accesses that I need to get my data, minimum and maximum, two level of page table? Two levels, no, four is too many. That's the maximum. So your answer is 3. 3 is the maximum, which is you go through the page level twice because you have two levels. And then the third time is a cache miss. So you go to DRAM to get your data. What's the minimum? 1. Without the TLB, you need to do page walk, right? Page walk, go through all levels of page table. So at minimum, you need to go to DRAM twice. The first level and the second level. Then you hit in a cache. So you go to the cache and don't have to go to DRAM. So to get your data, you go to memory 2 times. So minimum is 2, maximum is 3 for 2-level page table. In here, if you think about that, right? If you have the, okay, again, please. Sure. So let you should think about it this way. When you do a page walk, right? So I'm gonna go back one slide over here, right? This is 2-level page table. You're with me, right? That these are 2-level. This is 2-level page table. The first level in red red, right? Whatever. Oh no, the black color is the first level. The green is the second level. Both the black and the green are in DRAM. Those page table are in DRAM, right? So to get your physical address, you need to go to the black page table, then the green page table. Those are two accesses to DRAM. Yes. If you want to check the content of the cache, you need to get the physical address because remember the VIPT cache, right? That you need the physical address for your tag. To get the physical address, you need to go to DRAM. So to check whether your data is in the cache or not, you need the physical address. If you don't have the TLB, you need to go to the DRAM twice already just to get the cache, just to actually use the cache. Right? So are you with me on that? So at minimum, you need to go to the first level, the black thing, right, over here, and the second level, the green things over here. Those two DRAM accesses just to look into the cache. Then if it's a cache miss, you go to DRAM. So that's why the minimum is 2, maximum is 3. On your exam, I can ask you many level page table, right? So you can extrapolate this answer by thinking, if I need to actually do page walk, how many DRAM access that would happen? Afterward, don't forget that you still need to look up your data because you just have the physical address, you still don't have the data. So that's the third access. That's the last access you have to do. All right. So for the 64-bit machine, yes. So for the 64-bit machine, if you do not have the TLB, minimum is 4. If you have the TLB, what's the minimum? Minimum is so one access means that you hit in a TLB, but you don't hit in a cache, right? You go to DRAM to get your data. Can you do better? Essentially, you can, right? If your data is in the cache, then you go to a TLB, yay, it's hit. I know the physical address. Then you go to the cache, yay, the data is in the cache, so I never have to go to DRAM. Right? So are you with me on that? Basically, if you hit in a cache and the TLB at the same time, then you don't have to go to DRAM. And I can guarantee you with most of your program, yes, so the minimum is 0. If you have everything here that we talk about so far, minimum is 0. And I can guarantee you that most of your program, definitely more than 95% of the time you are in this category. You hit in the cache and you hit in the TLB. Right? From real program. This is the data I've seen all the time. Like unless you're going crazy with how you write your program, then you are hitting in the TLB and the cache all the time. These change a little bit with some certain application. How many of you about the graph algorithm? Or like if you're in the data structure or algorithm class, have you learned like some graph algorithm yet? Yeah, so for those of you who heard about graph algorithm, you can talk to Ajahn Kanat and ask about the how cache friendly is the data when you have to use graph algorithm, because this is a big research topic basically. You want to make sure it's cache friendly because from the algorithm it go to many different directions, many different edges, different vertices. It just turns out that the size is getting too big, so you can't cache them. All right, so your answer, let's say you heard about graph algorithm, but you still don't get it. Feel free to drop by our office hour. I don't mind talking about algorithm class. It's fun. So yeah. Anyway. So let's put everything together. This is going to be the repeat of the end of last lecture where you have the instruction here, right? You have load, which is read, right? And store, which is write. Right? And then you have DRAM. One thing I want to have like the divides here is like, okay, this is the cache, and this is the virtual memory, right? The TLB. When you have the load, right? When you have the load, what do you do to load your data? You go to the cache, right? So both load and store here would check the cache. Right? If they are in your cache, you get the data. If there's not, check the next level of the cache. If you buy a processor these days at 3 levels, because you can afford to put more things in your cache. That's why it's good to have the small technology like 7 nanometer, 10 nanometer that allows you to put a big L1, big L2, and really big L3. If you're stuck with like a 65 nanometer, then you might be able to afford like a smaller L1, smaller L2, and that's it. You can't fit that many transistors in your processor. Right? So with nowadays processor where you're going toward like 14 nanometer, 10 nanometer, 7 nanometer, you have L1, L2, and L3 caches. If you buy a really fancy machine, you might even have the on-chip DRAM, right? When you look at the cache, right, is this virtual address or is this physical address for the part that's going to L1? If this thing is virtual address, right? How about this? Is this virtual address or physical address? All right, let's not answer that question yet. Is this virtual address or physical address? The one that goes to DRAM. Physical address, right? Yes, physical address. Because once you need to go to DRAM, you need to know the physical address. If you don't know the physical address, too late, right? If you assume, so right now let's assume VIPT, virtually indexed, physically tagged. This is a physical address because you need to go to DRAM, right? Any questions about this? What about the first part? The one going into L1. If I use virtually indexed physically tagged, do I need just the virtual address or do I need both? So you need the virtual address for the index. Do I need the physical address for the tag? Yes, you do. You need to get the physical address to get your tag, right? Okay, that's an interesting question. So one of the questions, do we even have the option of accessing DRAM with virtual address? No. Once you want to access DRAM, it needs to be a physical address. Basically, it would treat whatever addresses come in and will go to that address. If you zoom into DRAM, there are two inputs. It's called the word line and the bit line. Both of these input, you need the physical address to get the exact byte and then the exact bits. Right? So those have to become the physical address. For L1, because you need virtual address for the index, you definitely need the virtual address, but you also need the physical address for the tag, right? So you need both of them here. Are you with me that you need both of them because you want VIPT? VIPT means I use virtual address for the index, physical address for the tag. Then from L1 to L2, do I use virtual address or physical address? Or do I use both? If I assume that L1 is VIPT. Both is fine, but can I just get by with physical address? You can actually just get by with physical address. Yep. Yeah, you have a great hunch. Basically, one of your friends saying, "Hey, yes, I suppose." Yep, you can just get by with the physical address here, right? Because by this point, I have the physical address already, right? The benefit of VIPT is I start with virtual address. I don't know I start with virtual address. I don't know what's my physical address yet. So I'm gonna use the virtual address, the information that I have for now, to get the cache set. That's why in the L1 you can use VIPT. All right. So now, if we have virtual address from my instruction side, right? From my instruction side to the left side, how do I get the physical address? Because now to access L1, I need both the virtual address and physical address. So how do I get the physical address? What's the first thing I do? Now we're focusing on this part here. So what's the first thing I do? From virtual address, right? What did we just discuss? Where we assume that this is what will be going on your exam for sure. What is that structure name? TLB. Yes. Why do I need a TLB first? So this virtual address come in, right, to the TLB. Address. What do I get out of the TLB? What's the output? Yep, you translate virtual address to physical address. So once you're in here, you got the physical address. If this is a hit, right? All right, fat finger, I'm sorry, that's not supposed to happen. If it's a hit, you get the physical address come in as a second input into your L1. What if I miss in the TLB? If you miss into the TLB, you translate virtual address into physical address, right? So miss. So virtual address come in here to the page. We call it page walker, right? Page walker perform page walk. What does page walk do? So over here in DRAM, you have the page table, right? All right, my handwriting sucks, so let me rewrite it. Page table. Yes, so when you do this walking, let's say you have a two-level page table. Let's assume you have two levels so that I don't have to draw too many arrows. First level, go here. Right, first level. You get PTE of the first level, right? You then walk again for the second level. You get the PTE, page table entry, of the second level. Right? Once this is done, once everything here is done, that's when you get the physical address back to your cache. But that's not it. One last thing. What do you need to do one last thing at the TLB? So you just got your physical address, right? TLB is a cache, right? TLB acts like a cache. So what do? You just finished translation. You want to update the TLB, right? So this physical address, then insert into the TLB. If the TLB is full, eviction happen. So the old virtual page number get kicked out of the TLB. That's all. Right? That's all for this whole thing. Basically, to get your data in DRAM, you look up the cache. Because we use VIPT for the cache, it means that we need both virtual address and physical address to check whether my data is in L1 or not. To get your physical address, I mean virtual address, obvious, right? Oh, okay. That's a great question. So one of the questions we have over here right now is, does the TLB eviction work just like set thrashing? Set thrashing is a problem where you evict the old thing, but you keep evicting all the time. The TLB eviction, the default policy that you are going to see is LRU. So it would have the same problem of set thrashing. So it uses LRU policy or something like an LRU. So if you take a digital design class and you need to like somehow let's say you work at Intel, right? Let's say you work at Intel in Hillsboro, like where Intel lab is, and they're like, hey, can you implement the fancy TLB? Then you will realize LRU is actually damn costly to implement. I use a swear word on that. I'm sorry about it, but it is costly. What people do is they imitate. They imitate what LRU is supposed to do, and they have a policy that is closely looking like the version of LRU. I'm gonna cover that in detail in the architecture lecture. If I get to open the class, I'm basically I'm trying to see if I can open the architecture class next semester. Why is LRU so expensive? So what do you have to do in the LRU? You need to compare it. You need to find out which one is the last cache block that I access, right? So what do you need to do to do that? You need to figure out when is the last time I access my cache, right? Then you need a way to compare everything, right? A way to compare which one of these cache block is the oldest. How many of you go through the sorting algorithm? Oh, you did merge sort, right? So what's the big O of the merge sort? Oh, n log n, like n log n operations. It means that you have to compare n log n time, right? Wait, why is it log n? Am I missing anything? It should be n log n, right? Oh, okay. Sorry. So yeah, and log n, right? Which means that you need n log n comparator, right? Because everything you add on this costs some hardware. So you need n log n comparator to do like, let's say you have a 16-way cache. Then you need 16 multiplied by what's log of 16. That's a 64 comparator. That's a lot. That's a lot to just like compare and get the least recently used. That's why in hardware, sometimes we actually like approximate this thing with cheaper hardware. So over here in the LRU, what we would do is one policy we can do is like, just don't kick the most recently used one. Like that's one possible policy. It's easy to implement, right? Whatever is the last time you touch, you flip the bit to say, hey, that's the most recently used one. Don't kick that out of my cache. Right? That's simpler. So hopefully that answered the question about why is LRU so expensive in hardware. Basically, you need to search for the oldest one. And this searching, it means that you need to build the hardware to do the search on your chip. Right? All right, so let's come back to system skill. Definitely great question, and I love going sidetrack, especially on the topic I'm working on research-wise. The next thing that we should discuss, actually, I think the order is a little bit odd here. I think maybe I should have discussed virtually indexed, physically tagged before the earlier slide. But over here, let's talk about VIPT in a little bit more detail, right? And let's assume that the two policy that at least give you correctness, right? We talk about synonym problem and homonym problem. You can have homonym problem with virtual address only. So let's stick with either PIPT, physically indexed, physically tagged, and VIVT, right? No, VIPT, my bad, VIPT. Virtually indexed, physically tagged. What do you need for PIPT? To get the index, right? So basically, if you break it down, there are two tasks. Okay? Both of them need two tasks. First, get the cache set, right? So what is the information in PIPT that I use to get my cache set? The index or the tag? Do I use the index bit for the set ID, or do I use the tag bit for set ID? Index tag, index tag, index tag, which one? All right, everyone brain freeze. Yes, thank you, index bit. So for this first task in PIPT, is it from physical address or virtual address? Look at the name. So it's PA over here, right? And then over here is VA. The second task is compare the tag. Both of them are the same, compare the tag. Why do you need to compare the tag? The tag is used to make sure that this is your data. It's not some other random cache block that just happen to have the same index bits, right? So you use the tag to compare. For PIPT, do I use physical address or virtual address for the tag? It's PT, right? So physically tag, both of these are PA. All right. So in PIPT, what's my step one? What is the first thing I need? Assuming that I need the physical address for both index and the tag. The first thing I need is I need to get a physical address, right? Because I use it for everything, so I need to get that. So over here, you send VA, right, to the TLB, get PA, right? This PA would then use to get my set, right, the cache set. And then you use PA again, right, PA, to compare the tag. So think about it this way, it's like kind of like a three-step process. Get your physical address, right? Get your physical address, then get your set. If once you got the cache set, you compare the tag. That's the third step. Over here, you have VA. Right? VA is used to get your cache set. And then in parallel, at the same time, you go to the TLB, you get PA. The tag. Compare the tag. Right? So it's a 3-step process, but step 1 and step 2 can be done at the same time. Right? Step 1 and 2 can be done at the same time. All right, so the benefit here is exactly, yes, VIPT is faster because you can do both TLB lookup and grab the cache set at the same time, right? So you save that time. So in the end, if I ask you what's the benefit of VIPT over other policies, it's faster. All right, so the last concept that we briefly talk about is page fault, right? So one of the benefits here is virtual address allows virtually larger than DRAM memory, right? So if the page is not in DRAM, we call this a page fault. You need to actually go grab them from, we call this a swap space. Swap space is an area on your hard drive that store these pages. Right? And let's put page fault into the picture. And I'm going to try to draw it as simplest as I can, right? So you have memory access, right, that want to either load or store something into your DRAM. The first thing you do is to go to the L1 cache, right? L2 cache again, right? And then DRAM. And to do this, you also go to the TLB. And if it's missing the TLB, you do page walk. When you do a page walk, this is when you know that, hey, my page is not in DRAM. So you go to DRAM 2 times, right? Let's say it's a 2-level page. I deleted. Sorry. Let me redraw it again. I just accidentally hit delete. That you have access. Pen. Right? You want to access L1, L2, and then DRAM. And on DRAM, you also have the page table. And I'm going to draw this area, as I said, this is on the disk, hard drive. Over here, you go to the TLB. So these are all the same content as the previous slide. Let's put everything together, right? And this is the page walk. If your page is not in DRAM, what you do here is you go to the page table, right? First level. One thing that can happen, you go to the first level, you get this information, go to the second level, and over there, it would tell you that, hey, this page is not in DRAM. It's not in DRAM. Don't use this physical address. This physical address is not valid. The valid bit will be 0. It just tells you data is not in DRAM. So what happened here when you got all this question mark? What would happen? You have this area called swap space, which the OS, right? It would tell the OS. So this is OS. To go get that page inside the swap space. Put this in my DRAM here. Basically, once you do the page walk, you would then know if a page is in DRAM or not. If it's in DRAM, you get physical address. If it's not in DRAM, the OS would come in and say, all right, let me put this page in DRAM. Your computer would wait a longer time. If you open up, say, 10 Chrome tabs, and you might have noticed your computer is a lot slower. How many of you realize that? I think I asked this question like 20 times in this class now, and everyone always said yes. If you start having like 20, 30 Chrome tabs, right? This is what happened. The thread running some of those tabs would cause page fault. The OS would say, okay, fine, I'm gonna go grab that data from the swap space, put that in DRAM for you, because Chrome would exhaust your DRAM. Chrome uses a lot of memory. It would actually exhaust your DRAM if you have tons and tons of threads and tabs over there. So this is pretty simple if you think about it in this high level manner. Your page is not in DRAM, so when you do page walk, the page table would tell you, hey, my page is not there. All right, so if you think that only one tab already used 50% of the memory, something is wrong with your computer. It's either you have so little memory or something is wrong with the tab you're opening. So let me go sidetrack here now that you brought this up. Sometimes Chrome launch a lot of threads depending on what get open on that page. Let's say you're watching YouTube. YouTube, what do they need? They need to render your normal page, right? Then you need to render the video. The video then requires video decoder. The actual animation of the video requires another process to use the GPU to render the video for you. If you don't have the GPU, or if you use the on-chip GPU that comes with Intel processor these days, those things use the same memory as your DRAM. So that causes more pressure on your DRAM. So that's why sometimes it can get slower even with just one tab, depending on what you're running. And sometimes the web app that people use, sometimes they unnecessarily like ask for so much memory. So when you call malloc, think about it this way: whenever you call malloc, you're using the DRAM. You use a space that other program could have used, right? So whenever you write a program, this is one thing I want you to be, I guess, mindful about is, do you really need that data? Every time you have to call malloc, are you doing it the most efficient way that you can figure out? Otherwise, you might create an app that use so much memory and everyone would hate you at the end. Like, why is this program causing so much memory, eating so much memory, even though it's doing something so simple? Microsoft, yeah, actually, how many of you use Microsoft Edge so far? Yeah, so I agree with both comments. So I use Microsoft Edge for certain things because it is kind of pre-installed on my Surface. Uh, the interface sucks. I can't get over that. That's why I still like primarily use Chrome. But one thing that I realized is Microsoft actually hires so many engineers into that team because of the Internet Explorer like memes that they got. Yes, the IE is the never ending memes that you can always joke about, right? So Microsoft at some point are like this, they hate it so much, they hired a new team, rebrand this whole thing, write a browser that actually works. Yeah. So that's what they do. How many of you use Bing search? That's cool. Okay. Uh, So another thing that I've seen from the scientific paper about Bing search, I think they are actually getting better and better and better, and now they are actually data supporting that some some research suggests that it's actually now better than Chrome and Google search. And right now they are like a valid competitor, but because of again the stigma from the old Bing search, it's always going to look bad when you say, "Oh, okay, I'm gonna search it on Bing." Uh, so yeah. Again, sidetrack. My bad. Hopefully you had fun. All right. Any question from the material that we cover for this class? For at least for today, before I go into the lab or your assignment, because I want to make sure that everyone is on the same page. This is this is the first time brand new lab that I adapt from what I created with my advisor at CMU for the architecture class. I simplify everything, so it's a lot easier for you to work with. Right? You don't need advanced like C hacking knowledge to kind of finish the lab, but this lab should give a really good overview of how caching works. Again, by the way, because it's brand new, if you run into bugs or something wrong with the starter code, let me know so that I can fix it. Like I try my best to make sure everything works, but because it's brand new as well, I really want to make sure I incorporate all your feedback here. So if you find something weird with lab, let me know. What you need to do is build a really simple cache simulator, right? What is a simulator? Simulator basically is a program that behave and simulate what you want to build, right? So how many of you play like, okay, I'm gonna sound so old, like a roller coaster tycoon and all those like the sim and all those games? Yeah, it simulates something, right? It simulates either the theme park, it simulates like human living in a household like the Sims, right? You can have a game that simulate, for example, a truck simulator where you can go in and just drive trucks all day long. I actually played that for a bit, and it's oddly addicting. I don't know why. Uh, but yeah, this is what you're gonna build. Now you are going to simulate the cache. You write a program to simulate the cache. Uh, to make everything really simple, I'm gonna define the structure. Right, you're gonna have two levels of the cache. First level is a L1 cache, two-way 16 sets, and then the second level, four-way 64 sets. The policy instead of LRU, I'm gonna make you do something even simpler. It's called first come first serve. First in first out, right? A cache block get brought in. That would be the first cache block that get kicked out. Any question about the FIFO policy? The first thing that you brought in is the first thing that you kick out, basically. Once the cache is full, the first cache block that you bring in, that's gone. To simplify things and allow you to debug your program, I have another function that I put in there in the startup code to initialize your DRAM. Basically, when you have read accesses to the cache, right? DRAM is pre-initialized. So this is how it works, right? If you look at DRAM, this is address 0, address 4, address 8, address 12. Basically at the incrementing address going that way. The value here will be 0, 1, 2, 3, 4, 5, going onward. Basically, it's a 4 byte information starting from 0 at address 0 and go from there. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until the end of my DRAM. All right. Read and write, I would also assume that it's always in 4-byte chunks. This allows you to simplify. Basically, this is like a simplified version of the cache. It allows you to simplify the read and write functions. So that's an overview. To actually make it functional, right, you need some input, right, to simulate the cache. Okay, let me go back to the theme park, like roller coaster tycoon games, right? To actually make a functional park, you need human going into the park and things operating and everything, right? So over here, to make a functional cache, it need to model some program, right? We call this a trace. A trace is basically, I provide a startup code for that. This is basically, let's look at this as this is your CacheLab, right? Trace come in. A trace basically capture, right? Read and write accesses. You then model, right? There's no output really. There's like a built-in function to print the content of the cache, and that's all. And then the main function, if you download the code, you will find that I actually built in the printing that say, okay, we finished running the trace. This is the performance, the hit rate. No, not the hit rate. The number of hits is this many, the number of misses this many, and how many cycles it would take. Basically, that's a clock that keep going. If it hit in the L1 cache, that takes a certain number of cycle. If it hit in the L2 cache, that takes another certain amount of cycle. If it doesn't hit in the L2 cache, that takes the most number of cycle. And then at the end of the day, this get accumulated and it get print out. So we say, okay, if you run this program, the trace of this program, it takes X number of cycle. To check for correctness, there is a built-in function that also put in that print the cache. This is also done automatically. You can call print. It would print the cache in a hopefully good enough formatting that you can see what's going on in there. If it looks ugly, let me know. I can kind of keep improving it and update the starter code. This doesn't affect what you're doing. Basically, you can just copy and paste new, like the updated function in. Basically, it would print something like this. Set 0, set 1, set 2, dot, right? And then it would print like data and the tag in this curly bracket separated by this vertical line. So this would print out all your data and tags so you can use it to debug your cache, right? You can keep printing this and see, okay, if I do this insertion, if I do this eviction, data is now gone. You can see the content of my cache. Here is the basic hierarchy. That's for L1. So basically you can use a print for both L1 and L2. Yeah. And let me know if these like built-in function doesn't work as intended. Like let me know as soon as you notice that, because I want to make sure I give you the best like handout as possible, so I can keep improving this. I don't mind. Just let me know. All right. And also because this is the first time I run this lab, I think this is probably the first time in Thailand for anyone to have like this kind of lab. To be honest. So let me know. I'm trying my best to make sure that you get a proper like experience without the negative like overhead, I guess. It's actually a little bit advanced, but I think you benefit a lot from it. Here's the assumed hierarchy. You have trace coming in, right? And then you have L1 and then L2. and then DRAM. And over here, I assume this thing called inclusive cache. Which means that L1 is a subset of L2. Basically, if you have something in L1, that same thing would be, it would exist in L2. What does that mean? When you do insertion and eviction, when you have access, basically, when you have a read or a write, put that in both L1 and L2. Put that thing in both the L1 and the L2. Eviction, depending on the level, if you're evicting something from L1, just get rid of that thing. Delete, but basically replace it with the new thing you're inserting. If you have to also insert things into L2, just get rid of that thing. That's why inclusive cache is simpler to model. When you insert something into, when you access any address, put them in both the L1 and the L2. When you want to kick something out, get rid of that from that level and you should be fine. If you kick something out of L2, make sure that that same address get kicked out of L1. Why is that the case? Because L1 is a subset of L2. So if you kick something out from L2, make sure that same address doesn't appear in L1. All right. Then this is the part that you need to do. The first part is the really simple one. Look up. Basically, you check. Sorry. You check if your address is in the L1 cache or not. And then you check if it's in the L2 cache or not. This should be pretty simple to implement. So in here there are three functions basically that you need to do. Set ID, right? So you have the address coming in. What come out is the set ID. Any questions about this function? You take a 4-byte address, extract the set ID. Another function is you have the address, get the tag. Assume everything here are physical address. Just don't bring virtual memory into play here. Just assume everything, that address is the only thing you have. All right. Any questions about the two functions here? You need to figure out what's my set ID and what's the tag. The other two function is called L1 lookup and L2 lookup. All right. This would return 0 or 1 depending on whether it's a hit or a miss. What's the input of the L1 and L2 lookup? Again, address, right? You use address for everything. You can then probably now figure out that, okay, what you need to do here is to call this getSetID as a helper function and get the tag as another helper function to search my cache, right? In the code, you will see the cache is a 2D array. Basically, I simplify that as well. Cache is 2D array. Over here. So you don't have to instantiate anything. It's already been declared. Right? So that's the first part. The second part is you need to handle when you reading a request, whenever you have to read a request, what do you need to do? Basically, when you read something, you insert that cache block, right? You insert the cache block into both the L1 and the L2. This is what you do basically in the read process. You have address, you have the L1 cache, and then the L2 cache, right? You put this in data and the tag, right? You put them into both the L1 and the L2. If my cache is full, what do I have to do? So that's the insertion part, right? Insertion part is not that hard. Basically, you put that in a cache, you figure out which way you're putting in. If the cache, if that set is already full, what's the next thing you need to do? Eviction, right? You need to get rid of something from the cache, right? So there are two function calls that you need to implement: handling eviction for L1 and then for L2. For L1, use FIFO. First in, first out. For L2, also use FIFO. Any questions about the read and eviction? Basically, read insert things in the cache, but right before you insert, if that set is full, you need to pick which one you are kicking out. This is done through the eviction function. L1 eviction and L2 eviction is already in the skeleton code that I gave you. So just implement that function, and that's basically handle reading. All right, so we are done with the lookup, getting set ID, getting tagged, read, handling the insertion part where you have the read request, then handling eviction for L1 and L2. The last thing is handling writes, right? We haven't really talked much about writes, but right now we'll assume this policy called write-through policy. What does write-through mean? When you have a write, right, into the L1 and then into the L2 DRAM, right? What you do here is write-through policy. Whenever there's a write, you update the value on all cache level, right? So if this is a miss, it's pretty trivial. Basically, you put in the data on L1 and L2. If this is a cache miss, right? Put the data into L1, put the data into L2, then update the data in DRAM. If let's say this is a L2 hit, right? You put this data into L1, you update data into L2, then you update DRAM. If it's L1 hit, you update. You update all the three levels. And that's it for the write-through policy. It is the simplest policy that you can think of. Obviously, if you look at this, it wastes so much bandwidth because you need to send all this update downstream to DRAM. But we're not going to talk about it. Let's make it functional for this class. Testing your program, basically you can create your own trace of memory access. It's work like this. There are each line consists of three things. First item is number 1 or 0. If it's 0, it means that this is a read request. If it's a 1, this is a write request. If this is a read request, look at the next item, that's the address. Because a read request doesn't involve the data, basically this read request, just ignore this thing. If it's a write request, then make sure you update the content of your L1, L2, and DRAM with the data you're reading. All right. The last thing I want to bring up is this hidden extra credit, which is not actually print on the assignment for the reason that I want you to stick around for the lecture. This is the extra credit. Basically, you can get up to 20% more on your assignment grade on assignment 4, right? What you need to do is, first of all, copy a functioning cache. Once you're done with the main cache simulator, copy that, create a new folder called extra credit. Then what you need to do is now modify your eviction policy. Basically, any cache policy, instead of using FIFO, first in, first out, be creative and come up with your own policy, right? Make sure you write what you're doing in a separate text files, just so that I understand this is the policy that you design. If you implement something like an LIU, you get 5%. The skeleton code actually is built in for you to actually have functioning LIU policy. Then, if you implement something that perform better than LIU, by performing better, it means that it gets better cache hit rate, right? And the execution time at the end, it takes less cycle than LIU, you get another 5%. Afterward, for people who attempt extra credit, I'm gonna rank everyone based on the performance of your cache, right? You can get up to 10%. So this is the spectrum. If only one of you submit, by default, you get 10%. If two of you submit, one will get 10, the other one will get 5. If 5 people submit, that'll be the one that get 2%, 4%, 6%, 8%, and 10%. If more than that submit, I would have more people clustering toward the good half, like more than 5% than the lower half. So hopefully this encourage you to write a better cache. It's kind of like you all compete to like build a better theme park in like in games, right? In a simulation game. Now I'm just asking you to compete and build a good cache. One thing is I'm actually going to test your cache based on the trace of the real program because I do have those. For example, some of these real program that I do have are things like uh, uh, what would be the access pattern if I run bzip2, which is a common compression algorithm, or things like GCC, for example. And then based on that, your simulator would behave certain way. It would give you certain amount of cycles, and then I'm going to compare the results. How long does the lab last? So you have until the Thursday after the exam, the 23rd, to submit. That's the deadline. But if you still have that token that we talk about, you can get up to Friday. Basically, technically the lab lasts until Friday midnight, like the last day possible for you to submit. Does it answer your question? Oh, the assignment grade. Yes, it would be out as soon as. As soon as possible. I'm trying to grade out everything. I actually ended up with fewer students now, so it should be out a little bit sooner. So assignment 1 and 2 should be graded hopefully this weekend. And then assignment 3 should be coming up right after. Assignment 3 is actually simple to grade because we do have the auto grader. Assignment 1 and 2, there's no auto grader, so it's all manual. And then I need to kind of like dig through the code to make sure that, hey, if thing doesn't work as intended, are there things I can do to give you points across from what you're implementing? So hopefully that answered your question. I'm sorry it's been like taking quite long. I would try to do as much as possible. All right, so That's it. That's no before we leave today. That was from the last lecture, actually. So that's all for today. Any questions that I can address?